Welcome back. We continue our lecture series. In the last lecture, if you recall, for the oblique symmetric projectile, I was trying to give you those equations of time of flight, maximum height, range, etc. And then we tried to look at for complementary angles how these equations differ and how you can have a kind of jugglery among these variables. And I also tried to give you a couple of models whereby by knowing the angle at any given two instants of time, you can get anything and everything pertaining to the projectile there. Now, continuing our discussion now, I would go a bit ahead of it. Today's thing, I'm going to look at fixed target. There is a fixed target, say here, whose coordinates are x, y, for example. Now I'll give you various scenarios. You are at this point, so this is the straight line distance you have. Now, one by one scenario, I am looking at no gravity. With what minimum speed should you project the body in order to hit the target? Is a fixed target. Remember, you already given a condition, no gravity. That means what? No acceleration and no air resistance. We never consider resistance, etc. in kinematics, because we do probably in dynamics. Now, in this case, at what angle and at what speed? So, you can throw with any speed of your choice by aiming. Now, aiming is called straight line viewing. I'm aiming something means I'm straight line, I'm viewing. Now, don't take your barrel guns or these guns of these days. Everything is programmed there. What you see is not a straight line viewing there. No, that takes care of the curvature, everything there. So we are not into that kind of a situation. I'm only talking of a straight line viewing. That means I have a stone. You see, in our childhood, we used to, while walking on the road, we used to look at some of this tamarind tree or some other tree, and we get that intention to pluck some of those things. So you take a stone and then try to throw it. You miss it hopelessly. You keep trying. It's what we call as the trial and error method. And I'm sure at one stage you are going to pluck it, but then you couldn't derive any relation at that point of time, nor could you say that, no, hit like this only, etc. It's all trial and error. Now we are going to see precisely, in the absence of any such kind of resistance, etc., what should be the minimum speed and what should be the angle at which you should project it so that it will hit the target. This is what I'm going to give that analysis. Now look at this. I took no gravity at all. So no acceleration means this is uniform motion. Therefore, the moment you throw it will automatically go and hit the target no matter what is your speed. But you have to aim and hit it. So if somebody asks you at what angle, you know that this is x, this is y, this is theta. Therefore, you must throw it at an angle. Theta is equal to tan inverse y by x. If you go too slowly, it will go. If you hit it very fast, it will go very fast. That's all. This is the first scenario. Second scenario. Gravity is present. Now, projecting by aiming. That means straight line view and then you project. Gravity is present. What's going to happen now? You know that we have just learned that the whole thing may go something of this sort. I can't give you the exact picture here. It is definitely below. That means what? The target misses. The projectile misses the target by certain vertical distance. You could very clearly see. So I will write it misses the target. It will miss the target because acceleration due to gravity. How much does it miss the target? Now the gravity term is the culprit here. What are the equations if you write it in scalar notation? Immediately write these things. And then y is equal to x tan theta minus gx square by 2u square cos square theta. You get the point now? Now I am straight line view means tan theta is equal to y by x. And cos theta is equal to x by root of y square plus x square. Sin theta is y, because all this is the root of x square plus y square. So you can, as I told you, gravity means this term, this term. So these are the terms which are making the body to deviate from hitting the target. So by what distance it misses? It misses by, if you know time, I will put half gt square or gx square by 2u square. I told you, what is cos theta? X by root this. Cos square theta, x square by root of x square plus y square. I am writing it here by 2u square. Cos square theta is x square by x square plus x cancel. So it is g by 2u square root of. So this is the vertical distance by which this will miss the target. If somebody can ask you questions of this nature, you can directly get them from this. So second scenario is done. Now I am looking at a third scenario. In order to hit the fixed target, how you should project it? In order to hit the target, how you should project it? How you should project? You project in such a way, that means if I aim something like this, I rewrite this. If I aim something like this, so this is the target, I have to aim like this so that projectile passes through x comma y. So you must aim above the target. You must aim above the target so that this projectile passes through this point. They may ask a question like this. What is the condition for the body to pass through a coordinate x comma y? Or what is the condition for hitting a fixed target? They may ask. So this is how you have to aim above that. Okay? This is the third scenario. Now I'll come to this aspect a little later. Now the next point is, that is fourth point. The fourth point is aiming and projecting. Aiming and projecting at the instant the target drops itself. When you aim, that is straight line viewing, you project, The target is allowed to be dropped. Will it hit the target? Now, this is an interesting part. For example, you say this is the target. Okay, if you are aiming at projecting, how much would you miss by that? Half gt square. Suppose if the target drops itself in the same time t, where does it fall? Exactly half gt square. That means whatever it is likely to miss, same thing is covered by something like this. Same thing is covered by this dropped body. Remember, dropped body or the dropped target. Then it will definitely hit the target. This is the fourth scenario. I'm now going to the next scenario. A freely falling body is aimed and shot at. A freely falling body is aimed and shot at. A freely falling body is aimed and shot at. Will it hit the target? Now, when you draw like this is where it is already falling with certain velocity, and this is how you are viewing. That is straight line viewing means straight line viewing, and it is not dropping itself, mind you. If it drops itself, it will definitely hit the target if the body is thrown in the same plane. That is obvious. Now, by the time when you start throwing, at that instant this body possesses certain downward velocity. Therefore, in the time it comes here, it will cover by Vt plus of gt square. That means the projectile is here and the target will be below the projectile. So it will miss the target. There is a clear-cut distinction between this case and the previous case. Never get carried away with freely falling body. Freely falling body, when you see it is already falling, then you are aiming, right? So be very careful. And in fact, what is meant by freely falling body? The body's motion is under the exclusive influence of gravity. We'll call it as freely falling body. Okay? So, because it possesses certain initial velocity, it will miss the target. Okay? Now, right. Now coming back to a very important thing that I'm going to do. Generally, not many books cover this part. Out of interest and curiosity, I think you can go through this analysis, but the end product is important rather than the process. But I do the whole process here. Say, for example, there is a fixed target whose coordinates are x, y. Supposing if my projectile is going through that point, that means this equation must be satisfied with xy. So the same xy I am taking it as like this. Two u square cos square theta. Alright? Now I'm going to rewrite this. 1 by cos square is sec square theta, secant square theta. And if it is secant square theta, that is 1 plus tan square theta. Therefore, I can write x tan theta minus gx square into 1 plus tan square theta by 2u square. Now I am rewriting 2u square y is equal to 2u square x tan theta minus gx square minus gx square tan square theta. I have cross multiplied and then written down. Now the whole thing I write in terms of tan square theta. I brought it onto this side. gx square minus 2u square x tan theta plus gx square plus 2u square y is equal to 0. Now I divide with gx square throughout. On this side it still becomes 0. So I'm rewriting this tan square theta minus tan theta into 2u square by gx, because x gets cancelled. This is plus 1 plus now I have brought it down to a simple quadratic equation in tan theta. What is it that we are trying to find out here? I have projected a body that is passing through a coordinate called x comma y, or if there is a target, it is going to hit the target. That means this must satisfy this equation of trajectory. So I substituted the xy there. So for this equation to be valid, your tan theta roots must be real and positive. If it is real and positive, yes, it will hit the target. You understand the consequence here? So what we will do here is write the generalized expression for tan theta. What is tan theta? Minus b plus or minus under root of b square minus 4, a is 1, c minus 4 into 1 plus 2u square y by gx square whole divided by 2a. Because it's a very lengthy equation, don't get confused, simply follow blindly. 4 if I take common, it becomes 2, and 2 if I take common, it will be here, this 2 gets cancelled. Now that will give me a relation is minus u square by gx plus or minus. Now what are we getting here? G square x. I'll write it here to avoid confusion. Minus 1 minus 2u square y by gx square. I'll multiply and divide with g there, so that this denominator I want to make it in a similar way here also. I write g square x square by g square x square. Now I can write this as minus u square by gx plus or minus under root of u raised to 4 minus 2u square gy minus g square x square by dx. I took g square x square out of the square root there. Now I got this. This is a little complicated expression for you. What is the condition? Now let us recall the condition that we kept for this body to go and hit the target or pass through that point whose coordinates are x comma y, is that this solution of tan theta must be positive and real, right? Real means what? This should be greater than or equal to 0 under the square root. So, for tan theta to be positive, u raised to 4 minus all this should be greater than or equal to 0. If that is greater than or equal to 0, then you will get, I think minus b means this is u square by 2gx. In the equation there is already negative sign there, minus b when you take it, it becomes plus. try to correct it in the previous expressions as well. So you have got this expression now. Now in such a case, tan theta becomes u square by gx. So if this is equal to 0, I'll write it here. U raised to 4 minus 2u square gy minus g square x square. If it is 0, then tan theta is equal to u square by gx. Right? Otherwise, we know that the tan theta general expression I will write here u square by gx plus or minus u raised to 4 minus 2u square gy minus g square x square by gx, right? So that we need not have to look for anything else at any point. They will be useful. Now coming to this is at another quadratic equation in u square, and it is not equal to 0 here. If it is greater than 0, I will again write u square is greater than or equal to minus b, that is 2gy plus or minus under root b square minus 4ac whole divided by 2a. Right? Now 4 as before it is common, so I can write g also common. 2 gets cancelled. Y plus or minus. This should be u square. Since this is always more than y, negative sign is not valid because this is a square term. So you will have only positive sign there. Now this is very important. U must be greater than or equal to g into this is a critical value. So the critical value is equal to under root of, this is important for you. That is the minimum speed with which you should hit the target, compulsory. Now, what is the condition? U must be greater than or equal to UC. You got that? That means if U is equal to UC, that means I am projecting it with minimum speed, then tan theta must be how much? U square, that is g into y plus root of x square by gx. G gets cancelled. This is the theta. If you project with minimum speed, there is only one angle at which you can hit the target, and that is this. Supposing I take u is greater than uc and you fix it. Suppose uc, let us say you got it as 22 meter per second. I want to take 30 meter per second. If I substitute 30, then you will get tan theta is equal to this plus or minus this. That means you are getting two angles. You are getting two angles at which you can hit the target. So be careful. If u is greater than uc, then for every u, there are two angles with which you can hit the target. With which you can hit the target. You understood this? Now, what is important for you? This is important and this is important for you. Well, if anybody can memorize this, the procedure may not be useful to you, but one should understand that in order to hit the target, this is the thing that you have to always remember. Now, just as you have got Still, I'm continuing with the same symmetric projectiles, oblique symmetric projectiles. Now you have y is equal to x tan theta minus gx squared by 2u square cos square theta. Suppose you have got y is equal to x tan theta minus all this. Now, it's a sheer jugglery, nothing else. How many ways you can write this, I'll show it to you. Y is equal to, if I take x tan theta common, gx by 2 u square cos square theta tan theta. Tan theta will be in the denominator. Okay? X tan theta. Now this will be sin theta by cos theta. 1 cos theta gets cancelled. So how you can write this? X tan theta 1 minus gx by u square sin 2 theta. Sin by cos gets cancelled. 2 sin theta cos theta is sin 2 theta. Now this g, I can bring it on to the denominator. Now look at this expression. What does that represent? That is nothing but your range. Therefore, x tan theta into 1 minus x by r. Beautiful. This is one very, very important result for you. Very important result for you. As I told you, you can make as many juggleries as possible whenever the trigonometry functions are involved. You see? Now I'll go a bit further into it. I'll write it as y by x is equal to tan theta into r minus x by r. Or tan theta is equal to y r by x into r minus x. Now I can write this as y by x plus y by r minus x. You can see that y by x plus y by r. So if you take LCM, x and r minus x and x gets cancelled, you will get this. Right? This is another way that you can write your expression. Now, what do you mean by this in this oblique symmetric projectile? Suppose this is my x comma y. Now, this is x. Obviously, what is this? R minus x. And what is this? Y. So, if I construct a triangle, that means I am projecting a body from a vertex of the base of a triangle to reach the other vertex of the base by grazing past the third vertex. I mean, when you write it, it looks a little complicated, but if I put it in pictorial form, now you can easily follow that I am projecting a body, it should touch all the three sides of that triangle. That's the meaning of it. Now, if I take this angle as alpha, if I take this angle as beta, and if I take the original angle of projection as theta, what is tan alpha from this? Y by x. What is tan beta from this? Y by r minus x. Now look, you got both from there. So, I can write directly tan alpha plus tan beta. Right? So I can put it as tan alpha plus tan beta. This one. So many ways, I mean, you can try to write them. Okay? You got this point? Now I erase this. Now, Based on this, you see, for example, I take a regular hexagon. Look at. Now, I am projecting a body. This is a regular hexagon. You are projecting a body from a distance in the horizontal such that it grazes past the four vertices of the regular hexagon. If the side is D, what is the range of this projectile if u is your speed of projection? Now, this is the kind of a problem. Just now we saw that there is a triangle that we have put it there with all the three vertices that was grazing past. In this case, it is grazing past the four vertices, how we should go about it. Now, these two are symmetrical. If you see, let this be x, this distance. Let this distance be x, okay? And this is D. What is this angle? You see, this angle is 120 degrees. This is 60, therefore this is 30 degrees. So this is D sine 30, therefore this part is D by 2. In a similar way, this is also D by 2 and this is x. So what is your range? X plus D by 2 plus D plus D by 2 plus x. 2x plus 2D or 2 into x plus D. We have to get that x value now. That's how we have to do it. How to get that, I think one has to think. Now come to this coordinate. What is this coordinate? You can see. What is that coordinate? This is the x-axis, x. And what is this? D cos 30, D root 3 by 2. So x comma D root 3 by 2. Okay? And if I come to this coordinate, x plus D by 2, and this is D root 3 by 2, this is another D root 3 by 2 by analogy. So that becomes D root 3. X plus D by 2 and that is D root 3. Okay? Right. Now, you got two equations, two coordinates. So you can substitute in an expression that we have derived. I'll do that again for you. Y is equal to x tan theta into 1 minus x by r. Now, y, what is y in this case? X, of course, is x. Y is d root 3 by 2 is x tan theta into 1 minus x by r. What is this? D root 3 is x plus, now, d root 3 by 2. D root 3 by 2 is equal to x tan theta into 1 minus x by r, and d root 3 is equal to x plus d by 2. This is x plus, isn't it? X plus d by 2, and then this is d root 3 tan theta into 1 minus x by r. Now it is a question of jugglery to get x.